Okay, so in this problem we have the integral of 4 secant h of ln of x divided by x integrated from 1 to square root of 3. And we're going to tackle this problem twice. We're going to do it in two different ways. One, we're just going to simplify using the definition of the hyperbolic function secant. And then in another one, we're going to do a u substitution with u is equal to ln of x. Okay, so let's start this. So by definition, we know that secant h of x is equal to 2 divided by e to the x plus e to the negative x. Okay, so if we plug in an ln of x into that, so secant h of ln of x is going to be equal to 2 divided by e to the ln x plus e to the negative ln x. Okay. Now, when you have a natural exponential function and a natural logarithm that get together like this, they cancel each other out. Okay. So this one is just going to turn into an x, and then this one you'll have to take the negative exponent and bring it up first. Okay. So bring up that to make it a -1, and then it's the e and the ln will cancel and leave x to the -1. So plus x to the -1. Okay, so that's what happens when you plug in an ln of x there. Okay, so let's use that to rewrite this right here as this. Okay, so we have the integral from 1 to square root of 3. Let's put our 4 out front there. And then we have 2 divided by x plus x to the -1 divided by the x, that's the one that was already there, right? And dx. Okay, now we can take that 2 and bring it out to the front as well. We could also, since this is a complex fractions are fractions within fractions, we could put a little over 1 here, there, flip and multiply the bottom. Okay, so when you flip it and multiply, you'll multiply by 1 over x. Let's take the 2 out front, make that an 8 out front. So 8 times 1, or the integral from 1 to square root of 3 of 1 over x times x plus x to the -1. Okay, so I just flipped this up, which means it was on bottom. The 2 came out. So here's what you got. If you distribute this right here, you get, let's rewrite that again, 1 over x times x is x squared, and then x times x to the -1, well, x to the 1 power and x to the -1 power mean x to the 0 power, which means it's just going to turn into a 1. Let's not forget our dx's here. Okay, so it turns into a 1. Now we're going to use the integral formula. I'm going to write it down over here. So we have this formula that says you have the integral of dx over a squared plus x squared. It's equal to 1 over a times tangent, or inverse tangent, excuse me, of x over a plus c. Okay, so if we look at our problem, our a is 1. 1 squared is the same as a squared, and of course you have your x. Okay, so we can use that formula, and now we can just write down our answer, which is, we need to keep our 8 out front, and then we have 1 over a, so 1 over 1, tangent inverse of x over 1, and we're going to integrate from 1 to square root of 3. Okay, so that gives us 8 tangent inverse, let's keep a parentheses around that, of x integrated from 1 to square root of 3. Okay, so let's plug those in. So we get 8 times tangent inverse of square root of 3 minus tangent inverse of 1. Okay. Now you should have a unit circle handy. You may already know these values. But if you look on your unit circle, where is tangent equal to the square root of 3, and we're looking in that first quadrant, it is going to be at pi over 3. So we have 8 times pi over 3 minus, and where is inverse tangent equal to 1? That would be at pi over 4. Okay, you subtract those by finding a common denominator. Okay, and you'll end up getting 8 pi over 12 once you distribute the 8, which reduces to 2 pi over 3. Okay, so there's the answer to that one. Now we're going to tackle it the other way and hopefully come up with the same answer. Okay, so our next one, we've got the same problem, except we're going to do a u substitution. Okay, so if we substitute u is equal to ln of x, that would mean that du is equal to 1 over x dx, and if we multiply over the x, we get dx is equal to x du. Okay. Your limits, you have to use this to find your limits. So u is equal to ln of 1, which is of course 0, and then u is equal to ln of square root of 3, which we'll just leave as that. Okay. So we rewrite our integral from 0 to ln square root of 3. Let's put our 4 out front again like we did last time. And we have secant h, the hyperbolic secant function, of u. And then, of course, we've got our x on bottom, and we've got our x du on top, which means that those x's cancel. That's the reason that we use the ln substitution, because this would happen. Okay, so you cancel both of those out. So you get 4 times the integral from 0 to ln square root of 3 of secant h of u du. Okay, so it looks a little easier. Let's see if it actually is a little easier. So we know that the integral of secant h, I'll write that formula down like I did the other one. So if you take the integral of secant h of x dx, that's going to be equal to inverse tangent of the absolute value of sine, hyperbolic sine, excuse me, of x plus c. Okay, so we can write that down, and then we have to put in our limits of integration. So we have 4 times tangent inverse times, or of the absolute value of sine, hyperbolic sine, and then we need to plug in u instead of the x. So u, close parentheses, and then this needs to be evaluated from 0 to ln square root of 3. Okay, so let's plug those in. Keep the 4 out front. We have 4 inverse tangent, absolute value, and let's put a parentheses around that 4. Absolute value of sine h of ln square root of 3 minus inverse tangent of sine, hyperbolic sine of 0. Okay, so it's not looking quite as straightforward. It's beginning to get a little more complex again, because we need to come up with a final solution for this. So what we're going to have to figure out is, what is the hyperbolic sine, and what happens when I plug in an ln of square root of 3? What happens when I plug in a 0? Okay, so we know that the definition of the hyperbolic sine of x is equal to e to the x minus e to the negative x over 2. Okay, so if I plug in sine hyperbolic ln square root of 3, that's going to give me e to the ln square root of 3 minus e to the negative ln square root of 3 all over 2. Okay, so just like we did in the previous problem, when the e and the ln get together, they cancel. So the first one is just going to become square root of 3. The second one, you need to bring this negative up and make it an exponent. That's logarithm rules. Okay, so it would be a negative exponent of the 3. So then it would cancel, and you'd get minus square root of 3 to the negative 1 power over 2. Now, square root of 3 to the negative 1 power simply means that you need to put this below underneath a 1. Okay, so that will become square root of 3 minus 1 over square root of 3 over 2. And if you combine, find a common denominator and then take care of this fraction, this 2 on bottom, it's going to eventually reduce into square root of 3 over 3. Okay? So that's what happens when I plug in ln square root of 3 into the hyperbolic sine function. Okay, so that's what I can put right here. Okay, now let's see what happens when I plug in a 0 into the hyperbolic sine. This should be a little bit easier to do. See, sine h of 0 is equal to, whoop, a little too close there, is equal to e to the 0 minus e to the negative 0 over 2. Okay, so these are 0 powers. This is going to be 1 minus 1 over 2, which is 0. Okay, so when I plug in a 0 into the sine h function, I get a 0 out. Okay, so now I know what to plug in place of the inside of both of these. So let me find a little room here. So I have the 4 out front, and then I have tangent inverse absolute value of square root of 3 over 3 minus tangent inverse of 0. Okay, again, you need to reference your unit circle for tangent. So where is tangent equal to square root of 3 over 3? That happens at pi over 6. And where is tangent equal to 0? That happens at 0, so minus 0. So you end up getting 4 pi over 6, which reduces to 2 pi over 3. So we got the same answer as we did the other way. I think the first way was a little bit easier than the second way, but both ways will get you there in the end.